The question before us says, consider the linear system below. If k is an arbitrary number, for which values of k does the system have one or infinitely many solutions? So we have a system of linear equations in three unknowns, and we have this k, interesting value k, and we are told that it's an arbitrary number. And so it can take on any value. And for some of the values that it takes, presumably we're going to have infinitely many solutions or not. So we have to investigate when it's going to have infinitely many solutions and when it's going to have one solution or any other permutation. So we can begin by elimination as usual. So if we label the equations as 1, 2, and 3, then we can try to eliminate x from equations 2 and 3. So if we subtract 3 times equation 1 from equation 2, what do we get? So equation 2 minus 3 times equation 1. What does that give us? Well, that gives us 3x minus 3x. So the x goes away. Then we get minus 5y minus 3y. That's minus 8y. And then we have 13z minus 3z. So that becomes 16z. And then we have 18 minus 3 times 2, which is 6. So 18 plus 6, that's 24. And we can eliminate x from equation 3 as well. So how do we do that? We can just have equation 3 minus equation 1. And what does that give us? X minus x, so x goes away. Then we have minus 2y minus y, that's minus 3y. Then we have 5z minus z, so that becomes 6z. And then we have k minus 2, that becomes k plus 2. So these are our two new equations. We've eliminated x from both equation 2 and 3. And we also want to eliminate y from the last equation. So we want to use this equation, let's call it equation 4, to eliminate y from equation 5. If we notice that 8 is a common multiple, 8 is a common factor of each term in equation 4, then we can divide through equation 4 by 8. So let's do that. Let's have equation 4 divided by 8. What does that give us? That gives us y, 8 minus y, plus 2z equals 3. So that gives us equation 6. So we can use equation 6 to eliminate y from equation 5. How do we do that? We multiply equation 6 by 3, and then we subtract it from equation 5. So we can have equation 5 minus 3 times equation 6. And what does that give us? Well, we have minus 3y minus 3y. So the y goes away. Then we have 6z minus 6z. 6z minus 6z. So that also gives us 0. Then we have k plus 2 minus 3 times 3. So k plus 2 minus 9. And this gives us 0 equals k minus 7. So after eliminating y from the last equation, we end up with 0 equals k minus 7. So our equations that remain are equation 1 and then equation 6. That's what we got after we divided through equation 4 by 8. And then we have this one. So Having reduced our system to these three, what conclusions can we draw? Uh, well, the first conclusion is that uh, in place of z, we now have 0 equals k minus 7. And 0 is equal to 0. 0 cannot be equal to anything else. So if 0 is equal to something, it must be equal to 0. That means that what we have here as k minus 7 must be equal to 0. If it's not equal to 0, our system is going to be inconsistent. So k minus 7, k minus 7 must be equal to 0. Otherwise, our system will be inconsistent. Else, our system will be inconsistent. So when k equals 7, then we have k minus 7 equals 0. So when k equals 7, our system is inconsistent. But if k is any other value apart from 7, then our system is inconsistent. So that's the first thing to note. The second thing to note is that when k equals 7, then we have 0 equals 0. So when k equals 7, we have 0 equals 0. That means that z can assume an arbitrary value, and we can use that to determine the values of y and x. And because z can assume any arbitrary value, we have infinitely many solutions. So that is the other scenario. When k is equal to 7, we have z assuming an arbitrary value. So we can set z equal to a parameter, z equals t, where t is a parameter. So t is a parameter, and we can use that to determine the values of y and x. So let's put z equals t in equation 6. And what do we get? We get minus y plus 2z, which is now 2t, equals 3. So what does that give us for y? That means that y is equal to 2t minus 3. And we can use this also to find the value of x in this situation. So the value of x is going to be, well, let's use equation 1. We have x plus y, but y is now 2t minus 3. Then we have minus z, but z is t, so this minus t equals minus 2. And what does that give us for x? That gives us x is equal to minus 2 plus 3 minus 2t plus t. And that gives us 1 minus t. So these are the three values we get. The first is x. X becomes 1 minus t. Then y becomes 2t minus 3. And z is t. It's free to assume any value. So this system of equations has infinitely many solutions when k equals 7. But when k is not equal to 7, the system is inconsistent, so it has no solutions. All right, let's look at another problem. Here we are supposed to consider another linear system, and we are told that if k is an arbitrary constant, for which values of k does a system have a unique solution? For which values of k does a system have infinitely many solutions? And for which values of k is a system inconsistent? So we have three equations. Again, we want to eliminate, first we want to eliminate x. So let's see, we label our equations 1, 2, 3, and we subtract equation 1 from equation 2. What does that give us? So equation 2 minus equation 1, that gives us 2y minus y, that's y. Then we have z minus z, so that gives us 2z, 2z. Then we have 3 minus 2, that's 1. So that gives us a new equation. We can call that equation 4. Then we subtract equation 1 from equation 3. Let's see what that gives us. So 3 minus 1, that gives us x minus x, 0, y minus y, also 0. Then we have this k squared minus 5z minus z. So what does that give us? That gives us k squared minus 5z minus z. So that becomes plus z. And then on the right side, we have k minus 2. So we can simplify a little bit this expression. What do we get? We have k squared times z. Then we have minus 5z. So let me write that. K squared times z minus 5z. Then plus z. And then what else? Okay, so that's equal to k minus 2. Then we can simplify further. If we notice this one, grouping like terms, minus 5z plus z, that gives us minus 4z. So we have k squared z minus 4z equals k minus 2. So if we pull out z here, then we have k squared minus 4z equals k minus 2. So what can we say? Let's call this equation 5. Now, if we notice that we can factorize equation 5, we have on the left side k squared minus 4. That's a difference of 2 squares. So we can write it again as k minus 2 times k plus 2 all times z equals k minus 2. And this is equation 5. We just factorized k squared minus 4 as a difference of 2 squares. So we are left with equation 1, equation 4, and then equation 5. So what can we do, or what can we conclude from these equations? One thing, because we are told that k is an arbitrary constant, it's free to take any values, we can try to see when is it going to make this side of the equation 0? Because when this side of the equation is 0, we need this side also to be 0. Otherwise, our system is going to be inconsistent. Or whatever value we have on the right side, we must have the same value on the left side. Otherwise, our equation is going to be inconsistent. So let's see how we can use that idea. So when k equals 2, what do we have? When k equals 2, then our right hand side here is going to be 0. And what's going to happen to our left hand side? It's also going to be 0. So when k equals 2, we have 0 equals 0. And when we have 0 equals 0, that means that z is free to take any arbitrary value. And if z is allowed to take any arbitrary value, then our system has infinitely many solutions. So when k equals 2, we have 0 equals 0, and therefore infinitely many solutions. Um, what about when k equals, let's say, minus 2? I'm using minus 2 because when k is equal to minus 2, this value on the left hand side is going to make the entire left hand side 0. So that's what we need to investigate. So when k equals minus 2, when k equals minus 2, the left hand side is 0. We have 0, but the right hand side, because k is minus 2, the right hand side is now minus 4. So in that situation, our system is going to be inconsistent because we have some value on the left that is 0, but on the right it's not 0. So we have this therefore, and therefore an inconsistent system. Inconsistent. All right, so we've seen what happens when k equals 2. We've seen what happens when k equals minus 2. Now let's see, what about a different value for k apart from 2 and minus 2? So let's look at, let's say, k equals 1. When k equals 1, we have k minus 2. That's going to give us minus 1 for this value. And then we have k plus 2. That's going to give us 3. So we have minus 3z, for instance. And we have 1 minus 2. That's minus 1. So when k is 1, for instance, we get minus 3z equals minus 1 for the third equation. And then we still have our first equation and our second equation. So here we can solve for z and subsequently solve for y and for x. So and we have the same situation for any other value apart from 2 and minus 2. So this is a system where, depending on the value of k, we could have a unique solution like we just did when k equals 1, but it's going to be the case when k is any value. Let's say k is 7 or k is 10. But when k is 2, we have the situation where the left-hand side is 0, the right-hand side is 0, and we have infinitely many solutions. And when k is minus 2, we have 0 equals minus 4. So there it's an inconsistent system. So depending on the value of k, we're able to see all the three scenarios that we have with linear systems. Interesting problem. See you later.